Okay, so an example of a PCR constraint. So let's see. The ones that I am generally most familiar with is, let's say I want to load up a trusted hypervisor. We're trying to build a trusted virtual machine system. And I want to make sure that my secret virtual machine data is only available if my trusted hypervisor is actually running. So what I would do there is I would establish a storage key where, one of the ways I could do this is I'd establish a storage key that says PCR 17 must reflect a good initial estimate measurement. And PCR 18 must reflect a good trusted hypervisor measurement. And now, if those two PCRs are correct, then I could decrypt my data. If all I cared about was that the hypervisor had launched. Or similarly, if I wanted to, and this is one of those kind of quirky ideas that somebody had. I talked about Flickr earlier, where you're using the dynamic root of trust for measurement to do basically a short single operation or a small number of operations. It has actually been proposed to use Flickr to do a virtual TPM that is a little faster than hardware TPM, where the keys that belong to this Flickr TPM would be encrypted to only be accessible if the PCRs reflected we'd had a good estimate and we launched Flickr with the proper Flickr TPM software. Does that answer your question? I'm using the DRTM a lot because it happens to be fairly convenient. It doesn't involve knowing what your bootloader is. I will also note that, so I've been kind of shorthanding that there's the dynamic root of trust PCRs and there's the static root of trust PCRs. There are 24 PCRs. 3 of them are dedicated to the dynamic root of trust for measurement. The first 15 or so are kind of hand-waved as being for the static root of trust for measurement, but only about 8 of them are actually defined. No history is preserved across reboots and PCRs. Every PCR is reset to 0 on reboot. So, as you say, if we were preserving history over time, we would rapidly get to the point where it is impossible to calculate or verify because what does it all mean? In general, we use PCRs to determine the current state of the machine or the state of the machine since boot. So now hopefully you can get a better sense of why those PCR constraints would be meaningful because it's reflecting the current state. Another thing that I will note is that you can use these also to limit when a key can be used during the boot process. So I've heard some people suggest things like, I want a key that is used by the BIOS or by the bootloader that is not freely usable later on. I'm not honestly sure why, I don't work at that level, but in that case, you can actually constrain a key such that PCR 0 through 3 may or may not have values, maybe you're not constraining them to them, but PCRs 4 and 5 must be 0. And now, as soon as the bootloader has run, you've filled in 4 and 5, that key is now unusable again. So not all PCR tricks have to do with, I've had a correct measurement. Some of them have to do with, nothing has been filled in yet.
Sorry, I got a question while he's typing. Tomorrow in the TPM programming section, is there going to be a lab machines which are given to us to use, or are we going to actually be doing it?
We're not actually doing it. When I did my survey of what people wanted out of the class, not a single person said they wanted to try TPM programming, so I took them at their word. If there is interest in doing a TPM programming class, I would be inclined to set that up as a separate thing, because frankly, 2 days is about the minimum I'd want to do that for anyway. Because every TPM programming class I've ever taken that's been like 4 hours long, by the end of the 3rd hour, about half of the class had managed to get started, unfortunately. Okay, so in terms of the different apps that can modify PCRs, the first answer is the first 15 PCRs, the ones that the static root of trust theoretically can use, even though some of them are not defined, anything can update them. So the thing about PCRs is that it is very easy to do a denial of service attack on many of them, because even if there's only one good value, all it takes is one extent to throw that out. This is generally not a threat that we worry too much about, because usually if something is decided to make the PCRs look wrong, something is wrong, you want to treat the machine as bad. See, fragility is a big thing here. In terms of the more detailed, what are the permissions, which PCRs can the DRTM affect, which can't they? The PC client specification does include the locality constraints imposed on all 24 of the standard PCRs. And in fact, I think I may even be talking about it tomorrow. I think I may even have that chart up to talk about which PCRs you want to use for what. I believe in the first section. So there you go. And indeed, as Nino says, there are not enough applications using PCRs that nobody has defined multiple PCR etiquette. It's not just for the initial few PCRs, it's for the small number of PCRs that we're actually really using. One thing that we do see, Matthew, is that of the limited number of applications that use PCRs, for example, the trusted grub for Linux, we do not have a good standard for what PCRs 9 through 13 mean. But the trusted grub documentation contains a standard for trusted grub for what it will put in PCRs 9 through 13. So that if you have determined that your bootloader is trusted grub based on measurements, and I don't actually know how hard that is to do, we haven't done studies, I can then say, given that I am using trusted grub, I will evaluate 9 through 13 based on trusted grub's documentation. There are only 24 PCRs and there are no standards. What we generally expect is that in an enterprise world, so few applications use PCRs that we don't expect collisions to be a big thing yet, and when we do see them, we need to standardize because they are a risk. Most applications, I would actually expect to be using resettable PCRs, which I'll get to tomorrow as to why. Resettable PCRs don't maintain history. So as long as no two applications are trying to access them at the same time, collisions are less of an issue because you wipe the history before you use them and then you wipe them again when you're done. That said, that is for a certain subset of applications. If you are trying to do an audit log, for example, you do want a non-resettable PCR, you're going to be tracking that over time, and yes, if you have multiple applications doing audit logs, you better hope they're not both in PCR 14, or at least that they're maintaining the same verification log of what ought to be in PCR 14. Okay, so the question is, the commands we talked about, are they only relevant for asymmetric keys? Yes, there are no TPM commands that use symmetric keys. None at all. Because of export control regulations. And if you think about it, a lot of these commands wouldn't make much sense for symmetric keys anyway. But no, there's no such thing as a symmetric TPM key, and there's not really a meaningful meaning for that. Yes. So the TPM can be used to decrypt stored symmetric keys, because stored symmetric keys are just data. And a lot of the reason I bring up symmetric keys is that in general, for encryption and decryption, we don't want to be using the TPM's asymmetric keys for anything longer than we need to. So what we'll often see is that we will encrypt a symmetric key and use that to then encrypt a larger quantity of arbitrary data, rather than trying to use the TPM to encrypt all of the arbitrary data. This is what we see in that privacy CA protocol, where I shorthanded it as saying we encrypt with the endorsement key, But what we're actually doing is encrypting a symmetric key with a wrapper that talks about what the symmetric key protects. And then we return the symmetric key so software can do the bulk decryption of the certificate itself. And we see that kind of structure used again and again in TPM applications because it's more efficient. So the symmetric key here is not generated by the TPM, it's generated by software.